Hello, this is Dr. Hanaa Assil, and this is a discussion of the questions of Unit 5 of June 2023 from the Pearson Edexcel International A-Level syllabus. So let's take a look at the questions and discuss the answers. The first question says the equation for a redox reaction is shown. What is the cell diagram for this reaction? How do we write a cell diagram for an oxidation reduction electrochemical cell? We look at the equation and we see where is the oxidation. So of course the oxidation is vanadium 2 plus to vanadium 3 plus. The reduction is copper 2 plus to copper. And we start writing the cell diagram from the left, starting with the oxidation part. So we find that the oxidation half cell is vanadium 2 plus, vanadium 3 plus. This is where oxidation happens. Now this is a mixture of solutions, so our electrode will be a platinum electrode. And then the other half cell has copper 2 plus to copper. So this is the reduction, and we have a salt bridge in the middle with two lines indicated by two lines. So this is how we write the cell diagram for this reaction. The platinum electrode, and then the solution of vanadium 2 plus, vanadium 3 plus, the salt bridge, that's the double line, and copper 2 plus to copper solid. Some standard electrode potentials are shown. Which reaction is thermodynamically feasible? How do we know if a reaction is thermodynamically feasible? First of all, we know that according to the table here, whatever has the first reduction electron potential is negative, then this is a better reducing agent. So in this list where we're going from electrode potentials negative and then positive, the ones on top are the better reducing agents. That means we're basically looking for something that is going from magnesium to magnesium 2 plus, or we can calculate the electrode potentials of each one. That is the oxidation plus reduction, and we look for the one that has an E cell that is positive. That would be the one that's feasible. So the only one that has an E cell that is positive is that last one. We do realize that when we're writing the E cell, or when we're calculating the E cell, going from cerium to cerium 3 plus, we look at the table. That is the opposite of what we have there. So if it says that the electrode potential for that equation is minus, we need the one that's opposite. So it will invert the sign, and that's plus 2.33. Then we need the one for magnesium 2 plus to magnesium. For example, we're talking about example A. Then this would be the total oxidation plus reduction. This would be the total, and in all the cases it is minus except for the last one. So that's the one that's feasible. In a chemical reaction, E cell is directly proportional to what? We should be familiar that E cell is directly proportional, first of all, to ln K, not K, so A is wrong. It is proportional to ln, natural log of K. It is also proportional to delta S total, since delta S total is proportional to ln K. So delta S total we know is equal to R ln K. So E naught is proportional to natural log of K, the equilibrium constant, and is proportional to delta S total, not the system, and not delta H. Okay, for the reaction shown, E cell is positive. Which statement can be deduced from this information only? Well, of course, if the E cell is positive, first of all, the reaction would occur. So A is wrong, the reaction would not occur, is wrong. E cell positive, the reaction is feasible. Then, are the reactants kinetically stable with respect to the products? No, they would be unstable. because they form products. The reactants are also thermodynamically unstable. Unstable means the products have lower energy than the reactants, so this reaction would proceed. Remember that kinetic stability has to do with the activation energy. Thermodynamic stability has to do with the delta H and the equilibrium constant. Which reaction occurs at the negative electrode in a hydrogen-oxygen fuel cell? You should be familiar with the reactions that occur in the alkaline electrolytes. These are the reactions that happen if the electrolyte is alkaline, and in acidic electrolyte, these would be the reactions that happen in the acidic electrolyte. And he's asking for the reaction that occurs at the negative. So the one that occurs at the negative is the one that involves hydrogen, not oxygen, and that first one would be a correct equation. Okay, which electronic configuration is correct? You should be familiar with electronic configurations of transition metals. Titanium, for example, is 22. Titanium 2 plus would have 20 electrons. And remember, when we remove electrons, we remove them from the 4s. So instead of having 4s2 3d2, it now has only 3d2. So what he has there is wrong. Chromium is 24, so it's supposed to be 4s2 3d4, but we said that this is an exception. We don't say 4s2 3d4 because we need just one more electron for the 3d to be half filled, so we remove one from the 4s, then both of them are now half filled, and that is the correct electronic configuration for chromium. Iron 3 plus. Iron is 26, so 3 plus means we have 23 electrons, and that means we're going to remove 2 of the electrons in the 4s. We don't remove the ones in the 3d, we remove the ones in the 4s, and then I still need one more. So instead of 3d6, which it was supposed to be at the beginning, it is now 3d5. Copper is 29. Again, we don't say 4s1, we don't say 4s2 3d9, we say 4s1 3d10, so that one actually is correct. Remember, we need just one more electron. It's supposed to be 4s2 3d9, but we don't say that because I take one electron from the 4s and put it into 3d, then the 3d is completely filled, and that is more stable. Structure of this complex is shown. What is the coordination number of chromium? Remember, we said coordination number is the number of bonds or dative bonds that are made to the central transition metal ion. Now, we're looking for coordination number of chromium, and that means I'm counting only one of the chromiums. I don't care about the other one. So each chromium has how many dative bonds attached to it? There are 6 dative bonds, so the coordination number of chromium is 6. Which complex contains only monodentate ligands? Remember, the meaning of monodentate ligand means the ligand that makes only one dative bond to the central metal ion. So the cyanide is a monodentate ligand. If we look at the oxalate, this is a bidentate. The EDTA is a hexadentate or a polydentate, and that diamino compound is a bidentate ligand. It has a chloride, which is monodentate, but it wants the complex that contains only monodentate ligands, so that's that first choice. Which complex has a metal ligand bond angle of 109? 109.5 means tetrahedral. So which of these is tetrahedral? Of course, the copper with 4 chloride ions are tetrahedral. So this is the one that would have bond angle of 109.5. The EDTA is a hexadentate, so this is basically octahedral. Silver ammonia complex is a linear structure with bond angle 180, and the platine, this is a square planar structure. Which ion is not blue? Okay, let's take a look. That first one is this. This is blue. Now, the cobalt complex is not blue. It's pink. The chromium complex is blue, and the copper complex is blue. So, the one that's not blue is the cobalt. Which equation shows a redox reaction in which the solution turns yellow? So, I want it to be redox, and I want the final color to be yellow. Now, if we look at that first choice, FeCl2 is green. So, and that's not a redox anyway. The second choice, that's yellow, but that's not a redox. The choice C gives the dichromate, which is orange. We're starting with the dichromate, which is orange, and we're forming chromate. But again, this is not. The chromate is yellow, but this is not a redox reaction. Now, in D, we are starting with the chromium hydroxide, which is green, and that gives a yellow, and that is a redox reaction, so that's my choice. Aqueous ammonia is added in excess to an aqueous solution of copper 2+. What is the equation for the overall reaction? So we're adding excess ammonia. Remember, copper 2+ in solution is a blue solution. When we start to add a small amount of ammonia, it gives a precipitate, a blue precipitate of copper 2 hydroxide. If we add excess, then we have the copper ammonia with 2 water. That is a blue, dark blue solution. So that is choice C. Which equation shows the formation of a precipitate? Remember, when we add zinc hydroxide in an acid, this would give the white precipitate of this zinc complex. What is the sequence of oxidation number changes for vanadium when V2O5 is used in the contact process? Well, let's remember, we said the contact process is what? The contact process is the process in which the SO2 reacts with oxygen to give SO3, and this is used to make sulfuric acid. So the role of the vanadium pentoxide is a catalyst. The vanadium pentoxide is reduced by the SO2 to give V2O4. And then the V2O4 is oxidized by the oxygen to give V2O5 again. So it is regenerated. And the overall reaction, if we multiply all this by 2 and then we add up so that we remove whatever is the same on both sides of the arrow, this is the final contact process, which is formation of the sulfur trioxide, which is then used to make sulfuric acid. Now, the question is, what is the sequence of oxidation number changes? What happened is the V2O5 changed to V2O4. V2O5 has vanadium plus 5. We changed it to plus 4, and then we oxidized it back to plus 5. Okay, question 15 says, what is the total number of delocalized electrons in anthracene? What is anthracene? It's actually 3 benzene rings together. So if you're going to draw it in the form of double bonds, we can either draw it like this or like this. And we're asked what is the total number of delocalized electrons. You should remember that each of these double bonds has 2 delocalized electrons in it. So the total number of delocalized electrons will be 2 times the number of double bonds, which is 7 double bonds. So 2 times that is 14. Which statement explains why bromine reacts more readily with phenol than with benzene? Well, we should know that phenol is more reactive than benzene, and that is because the lone pair of electrons on the oxygen are delocalized around the ring, so the phenol is more susceptible or would more readily undergo electrophilic substitution. So this is the reason why bromine reacts more readily. A lone pair of electrons on oxygen in phenol is delocalized into the ring. Which reaction can form a secondary amine? Okay, let's take a look. That first one has a cyanide group. When we reduce it with lithium aluminium hydride, it forms this kind of amine. And of course, you should realize that this is a primary amine. When the NH2 has both hydrogens with it, it's not replaced by an alkyl group. Now in B, we have this ethyl amine reacting with ethyl bromide. That means one of the hydrogens on the amine group will be replaced by an ethyl group. That means the amine now that we have is a secondary. So this is the one that is secondary. The choice in C already has two alkyl groups. Reacting it with another halogenoalkane would replace that hydrogen left with it. So that is a tertiary amine. And that last choice is hydrolysis of the amide with sodium hydroxide. So this gives me the sodium salt plus this amine, which is actually a primary. So the one that's a secondary is the one in B. Compound X reacts with excess nitrous acid, followed by coupling with excess phenol to form an azo dye. What is the structure of the azo dye? Well, let's see. If I'm starting with compound X and I'm adding nitrous acid, remember nitrous acid, that is sodium nitrite in presence of HCl. What does that do? It forms the diazonium salt. So this is the salt formed. We form diazonium salt. This is excess. So each of the amines will form a diazonium salt. Now we're reacting it with excess phenol. That means the phenol will attach to each of these diazonium salts. So this is our product. Which one of these is correct? That's the one in D. 4 amino acids are dissolved in deionized water to form separate solutions. Which amino acid would give the solution with the lowest pH? So lowest pH means most acidic, more acid groups. So this would be the one with the lowest pH. Which carbonyl compound and Grignard reagent would not react to form compound Y? Remember, we use Grignard to prepare inorganic synthesis, to prepare compounds. This is a reagent that would attack a carbonyl group. So which of these would not give compound Y? If you look at A, if I'm reacting the Grignard with that carbonyl compound, then this is what I'll end up with. So this is different from what we need. So this is the one that would not give compound Y. If you look at each of the other choices, attacking in the same way, it would form compound Y. This question is about mercury and its compounds. Mercury is a liquid element in the same group of the periodic table as zinc. The electronic configuration of mercury is given. Mercury forms compounds in either +1 or +2 oxidation states. Explain why mercury is classified as a D block element but is not a transition element. What do we mean by D block element? It means the outermost electrons are in the D orbital, or the final electrons that are added are in the D block, in the D orbital. And transition element, what does transition element mean? It's an element in the D block and it forms one or more stable ions with incomplete d orbitals. So let us look at mercury. Well, mercury in the +1 oxidation state, that means we lose the electron from the 6s, 1 electron from the 6s. Mercury +2 would be the 2 electrons in the 6s, but in both cases the 5d is full. It's not incomplete. So mercury is a d block element since the last electron is in this d sublevel. It's not a transition element since the ions do not have incomplete d sublevel. Mercury reacts with nitric acid to form an aqueous solution of mercury nitrate and nitrogen monoxide. The unbalanced equation is this. Explain using oxidation numbers why this is a redox reaction. Okay, so if we look at this, where is the oxidation? That's mercury goes from 0 to +2, and the nitrogen goes from +5 to +2. So this is redox because the reaction involves both oxidation and reduction, and you have to mention which one was oxidized and what are the oxidation numbers and which is reduced and so on. So mercury is oxidized from 0 to +2. Nitrogen is reduced from +5 to +2. Deduce ionic half equations for this reaction. So what do we have? We have mercury going to mercury 2+, and that means it has lost 2 electrons. So this is the first ionic half equation. Now, the other one would involve the nitric acid and the NO and H2O. So if this is the complete equation, when we balance it, this is the complete equation, balanced. We can divide all through by 2. So this would be the second ionic equation. But notice that we have nitrates on both sides. We have 4 nitrates before, 3 nitrates after. So we cancel them and we're left with 1 nitrate, and we'll need 3 electrons to balance the charges. So this is the final ionic half equation. Complete the equation for this reaction by adding the coefficients. So basically we are balancing. So if you start to balance, well, what do we have? We have 3 nitrogens after the arrow, so we'll need 3 in front of the HNO3. But then we need to balance the hydrogens. So now the hydrogens are not balanced, so we need to increase it, and you'll keep doing this until you find that this is what we need to balance this equation. Please remember how to balance equations. You should be able to do this. You keep counting before and after the arrow, and you increase the one that is less until everything is balanced. This compound is an explosive. It is produced in the reaction between mercury nitrate and ethanol. The other products of the reaction are ethanol and water. Write the equation for the reaction of 1 mole of HgNO3. So we're saying HgNO3 plus ethanol. Can you see how we write ethanol in an equation? Don't write it C2H6O. It's not C2H6O unless if you're required to write the molecular, if the question says write the molecular formula of ethanol, it is C2H6O. But when we write it in an equation, we need to indicate that this is an alcohol. So we write it C2H5OH to give that product that is given, and then plus it says it would give ethanol. Again, don't write ethanol as what? C2H4O. That's the molecular formula of ethanol. But when we write it in an equation, we need to indicate that it's an aldehyde, so it is something CHO. So ethanol is CH3CHO plus water. Okay, and this is the balancing of the equation. This compound decomposes as shown. Calculate the total volume in centimeter cubed of gas produced when 1 gram of that compound decomposes at room temperature and pressure. So we're starting with 1 gram of the reactant. So the first thing we need to do is get the number of moles. Number of moles is mass over molecular mass. That means we calculate the molecular mass of the HgCnO twice. So that is 284.6. Then we get the number of moles. So that is the mass given, 1 gram over the MR. That's the number of moles of the reactant. Now we're being asked about what? About the total volume of gas. Where are the gases? The equation says 3 moles of the reactant gives 2 moles of CO2 plus 2 moles of CO plus 2 moles of nitrogen. That's a total of 6 moles of gas. So 3 moles of the reactants give 6 moles of the gas, and that means the number of moles we have would give you need to multiply by 6 over 3. So basically you're multiplying by 2 to get the number of moles of gases, total gases, and then the volume is the number of moles times 24, since it says at room temperature and pressure. That gives it in decimeter cubed. The question asks for centimeter cubed, so you multiply by 1,000. Easy enough? Okay. Mercury 1 chloride is also known as calomel. A saturated calomel electrode may be used as an alternative to the standard hydrogen electrode. So, we did not study the calomel, but it gives me the basic setup of the calomel electrode. The half equation for this electrode is this. The standard electrode potential of the calomel is this. So just why KCl crystals are needed in the outer tube of the electrode? Well, let's look. What is the electrode made of? It's made up of saturated potassium chloride. So in order to keep it saturated, I need to have some crystals down there. So we have crystals to keep the solution saturated with chloride ions. A calomel electrode was used to measure the standard electrode potential of the tin 2 plus tin solid half cell. The reading on the voltmeter in this cell is plus 0.37. So the overall cell with the calomel is this. Deduce the standard electrode potential for the tin 2 plus tin half cell. Now we were given that the calomel has an electrode potential of plus 0.24, and we're saying that the calomel with the tin half cell is plus 0.37, and that means the tin alone is the difference between that, so that is minus 0.137. Write the overall equation for the cell reaction. Well, what do we have? We have the HgCl2 going to Hg. This is the one for the calomel. And the one for the tin is this. And overall, you need to cancel the electrons and then just add up everything before and after the other. Add labels to complete the diagram of a standard hydrogen electrode. So, for the standard hydrogen electrode, what do we have? We should know that what is going in there is hydrogen at 100 kilopascal and 298 Kelvin or 25 degrees Celsius. That middle box is pointing to the platinum electrode, and the solution in there is 1 mole per decimeter cubed of an acid, strong acid. So it's 1 mole per decimeter cubed of HCl or sulfuric acid. So just one advantage of using a calomel electrode in place of a standard hydrogen electrode when measuring a cell potential. So if I'm using the standard hydrogen electrode to measure the potential of, for example, the tin 2 plus tin half cell, then I will have this kind of setup. So what is the advantage of using the calomel? Well, one advantage would be that the calomel electrode does not require a salt bridge. connected directly. The amount of calcium ethane diuate present in a sample of spinach is determined by redox titration. 11.4 grams of spinach leaves are stirred in 50 centimeter cubed of a warm acidified solution of 0.01 mole per decimeter cubed potassium permanganate, oxidizing all the ethane diuate ion. Then the excess manganate, so we're going to allow the potassium permanganate to react with the ethane diuate. Now, any excess we're going to titrate in order to know how much is the excess, then I can determine how much reacted. So the excess manganate are then titrated with an acidified solution of iron 2 sulfate, and we found that it needs 25.95 centimeter cubed of iron 2 sulfate. Calculate the percentage by mass of the calcium ethane diuate present in the spinach leaves and give your answer to an appropriate number of significant figures. So basically what do we have? This is what he did. The spinach, we added 50 centimeter cubed of the acidified potassium permanganate, and then we titrated the excess permanganate. So I need to know the initial number of moles of permanganate. What did he use? He used 0.01 mole per decimeter cubed of 50 centimeter cubed. Remember, in all these equations, we need to convert the centimeter cube to decimeter cube, divide by 1000. So that's the initial number of moles that we started with. Now we reacted some of it with the ethane diuate, and the excess was titrated. So to get the excess, we can get number of moles of iron sulfate, concentration times volume. We are given the concentration of the iron 2 sulfate and the volume divided by 1000. So this gives the number of moles of iron 2 sulfate. Then I can determine from the equation, you can see that from the equation, 5 moles of iron 2 plus reacts with 1 mole of permanganate. So the number of moles of permanganate is the number of moles of FeSO4 divided by 5. And then that would be the amount that remained after reaction. So the number of moles that reacted would be the difference between the initial and the excess. So that's the number of moles of manganate. Now we go back to that first equation up there, and we find that 2 moles of manganate react with 5 moles of C2O4 2 minus. So the number of moles of the C2O4 minus would be the number of moles of manganate times 5 over 2, and this gives our number of moles, and we are required to get mass. So I can calculate the MR of CaC2O4 multiplied by the number of moles. This is the mass of ethane diuate in the spinach. He wants percentage. Then that would be this mass over the original 11.4 of the spinach leaves times 100. Is that okay? Okay, some thermochemical, X-ray diffraction and bromination information on benzene and cyclohexene is shown. So we're given thermochemical data about the delta H of hydrogenation. We're given X-ray diffraction data about length of the bonds, and we're given bromination about reactions. Explain how all this information provides evidence that the electrons in the pi bonds of benzene are delocalized. Well, let's take a look. This was the thermochemical data, and what it tells me is that the delta H of hydrogenation, that's adding hydrogen to a double bond. If we're talking about cyclohexene, it's minus 120. If we're talking about benzene, it's minus 208. Now, if we say that benzene has 3 double bonds, then the delta H of hydrogenation should actually be 3 times cyclohexene. So it should be minus 360. But it's not, because the double bonds are delocalized. So they're not actually 3 double bonds. They are less than 3 double bonds. They're about 1.5 total, 1.5 double bond. So the delta H of hydrogenation they actually found is minus 208, not 3 times the minus 120, and that is used as evidence to say that it's not really 3 double bonds, they are delocalized over the benzene ring. Now, the X-ray diffraction data has to do with the bond length, and it indicates that all the bonds in the benzene ring are the same length, while in cyclohexene, the length of the single bonds is more than, or the single bonds are longer than the double bond. And this again is used to indicate that the double bonds in the benzene ring are actually delocalized around the benzene ring. So in the cyclohexene, the single bonds are longer, while in benzene all the bonds are equal and longer than the double bond in the cyclohexene. So this indicates that actually it is delocalized around the benzene ring. Now, bromination, reaction with bromine, we realize that in benzene, if we're reacting with bromine, we need a catalyst. With cyclohexene, it is something at room temperature, no catalyst is needed, and this means that benzene is less reactive than cyclohexene. So, and it also reacts in a different way because the benzene does electrophilic substitution, while cyclohexene does electrophilic addition reactions. This question is about polymers. So we're given 2 polymers and we're told that they're water absorbent, and PAM is made from acrylamide monomer. Give the IUPAC name for this compound. How would you name this compound? First of all, it's an amide with 3 carbons. So it is prop and it has a double bond. The double bond, if we say that the carbonyl of the amide is carbon number 1, then the double bond is on carbon number 2. So the name of that is 2-propionamide. Explain why PAM is able to absorb large amounts of water. Include a diagram in your answer. Now, which one was PAM? This was PAM. Why is it able to absorb large amounts of water? Remember that to absorb water, it should be able to do hydrogen bonding with water, and there are several places in which it can form hydrogen bonds. It has the carbonyl, oxygen of the carbonyl group to form hydrogen bonds with water. The nitrogen can form several hydrogen bonds. So the fact that it can form several hydrogen bonds with water, add the NH part and the C double bond O part. The structure of PAA in aqueous solution is pH dependent. Below pH 4, the structure is compact due to formation of intramolecular hydrogen bonds. So it can form hydrogen bonds between its molecules, so it is compact at acidic pH. Above pH 8, it has an open coil structure. Now, what was the PAA? This was the PAA. Now, why is it that at pH 8 in alkaline medium, it would form an open coil structure? This is because in alkaline medium, this would be an oxalate, a negatively charged oxalate ion. So the molecules would repel each other. The negative charges on the molecules would repel each other. So they would try to get as far away from each other as possible. PVP is an addition polymer used in the pharmaceutical industry, and the average molar mass of PVP is this. Draw the structure of the monomer used to make this polymer. So if we're given the structure of the polymer, what do? We remove the bonds on both sides and put a double bond. So this would be the monomer from which that polymer was made. Calculate the number of monomers needed to make one molecule of this polymer that has an MR of 90,000. So what is the monomer? The monomer is one of these. So calculate the MR of the monomer. Now, how many carbons, hydrogens, nitrogen, and oxygen? That would be the molecular formula. Calculate its MR. The MR of one of them is 111. Now, we're told that the total is 90,000. So, divide that by 111. I find that I can get 811 of these units joined together to form a polymer. 740 milligram tablet of painkiller contains 4% by mass of this compound. Calculate the number of molecules. So we're still talking about that PVP polymer. So get the mass. The mass is 4% of the 740 milligrams. That would be 29.6 milligrams. You divide by 1,000 to change it into grams. So after saying that it was 4% of the 740, that means I have this mass of the PVP. Now, we said that the total molar mass of the polymer is this. So, how many molecules? You can get the number of moles. So, number of moles is the mass that we got over the molecular mass given. And then you should know that number of molecules is the number of moles times 6.02 times 10 to the 23. This gives you the number of molecules. Okay. All types of nylon are condensation polymers. What is meant by condensation polymer? Remember, condensation polymer like polyamides or polyesters, they are long chain molecules made by joining many small molecules together. Now, in condensation, the monomers have active groups on both ends. Remember, we have addition, in which the monomer is an alkene or is unsaturated. But in condensation, the monomers have active groups on both ends. So we have diamine or diacid. And they are joined together by removal of small molecules. So, for example, we remove an H and an OH. So, the other molecule removed here is water. The structure of nylon is shown. Nylon is made from two monomers. Deduce the structural formula of these monomers. So, of course, the part that has the carbonyl can either be an acyl group or an acid group. So this would be the structure of that first monomer on the left. Now the monomer on the right is a diamine, and we put the number of carbons in the middle, either in this form or drawn CH2, 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 and so on. So this would be the structural. The question requires structural formula of the monomer. This compound can be directly converted to give a different polymer. So this is an amide. If I open the amide, then one end would be acid and the other would be amine. So I can connect it to another molecule like itself. So these are two molecules in which the acid of one is connected to the amine of the other. So this is what we call nylon 6. The synthetic drugs of the cane family are used as local anesthetics. Cane drugs prevent nerve activity by binding to sodium channel receptors in the lipid cell membranes of neurons, whatever. Okay, what is the question? Name the 3 functional groups present in benzocaine. This was benzocaine. What are the 3 functional groups present? Well, let's see. We have an amine group. The benzene is an arene, and the ester group. Procaine can react with hydrochloric acid to form a monohydrochloride salt. So write an equation using molecular formula for this reaction. So what are we starting with? We're starting with this one. So I need to determine what is the formula. So this is how we decide the formulas. We look at the number of carbons, number of hydrogens, and so on. So this comes out to be this formula. We're reacting it with hydrochloric acid to form the monohydrochloride. Monohydrochloride means the lone pair of electrons on that nitrogen on the right is acidified, so it becomes NH plus Cl minus. So we're adding an H and a Cl to that original formula. Explain by considering both nitrogen atoms which nitrogen is more likely to be protonated in the reaction with hydrochloric acid. Remember which of these has the lone pair of electrons available. The amine on the left would have its lone pair of electrons delocalized into the benzene ring, so it's not available. This one has its lone pair of electrons available to make a dative bond with the H+, so this is the one that would react. So the N of the amine bonded to the ethyl groups is more likely to be protonated. This is because, first of all, the ethyl groups are electron donating, so the lone pair of electrons on the nitrogen are available to form a dative bond, while the nitrogen on the benzene ring has its lone pair of electrons delocalized on the benzene ring, so they're not available to make a dative bond with the H+. When benzocaine and procaine are hydrolyzed, one of the products formed is the same. So if I hydrolyze these two compounds, which product is the same? Can you see these? Now, if we break them, both of them will give this part. So this would be the acid group. Lidocaine can be prepared in the synthesis shown. So we have a series of syntheses, and the first question is give the mechanism for step 1. What is step 1? This is adding a nitro group on the benzene ring. Remember that this is electrophilic substitution. We react it with concentrated nitric acid in presence of concentrated sulfuric acid. This is because the nitric and sulfuric will form the electrophile, which is the NO2+, and then this is attacked by the benzene ring. So it is added onto the benzene ring, and then the electrons, please note the intermediate in the middle, the electrons between the carbon and the hydrogen are used to return the benzene ring to its original structure. You don't bring the arrow from the hydrogen, the arrow is from the bond, the electrons between the carbon and the hydrogen. So this is the mechanism of the reaction. Then the question says a low yield of this product is obtained in step 1 due to the formation of additional organic products. This is not the only possible product that I can get. Give structures of 2 other possible products. So if we're trying to add a nitro group on that benzene ring, it could give me that product, but it could also put the nitro on other places, for example on this carbon or on this carbon. So these are 2 additional byproducts that could be formed. Give the reagents for step 2. What is happening in step 2? The nitro is being changed into an amino. How do we do that? We add we react it with tin in concentrated HCl. That would change the nitro into an amino. Deduce the skeletal formula for the reagent for step 3. What are we reacting that amino group with? We're going to react it with something that has this group, so we use the acyl chloride to react to form that product. State the type and mechanism of reaction occurring in step 4. What is happening in step 4? The lone pair of electrons on the nitrogen are attacking that to displace the halogen, so this is nucleophilic substitution. This compound is chiral. Indicate the chiral center. Where is the chiral center? Remember, the chiral center is a carbon that is bonded to 4 different groups. So if you look at the structure, this is the only carbon that is bonded to 4 different groups. Remember that the 4th one is a hydrogen. So that carbon has bonds to the carbonyl, to the nitrogen, to a methyl, and to a hydrogen. Articaine is metabolized in the body with a half-life of 20 minutes. A patient is given a dose of 100 milligrams of this compound. Calculate the mass of articaine in microgram remaining in the body after 4 hours. Remember half-life? Half-life is the time taken for half of it to remain. So after 4 hours, how many half-lives is that? The number of half-lives is, you're going to, this is 4 hours, so you change it to minutes, multiply by 60, divide by 20, so this is 12 half-lives. And that means every half-life of this, the mass becomes half of it, and so on. So what would be the final mass? Remember, the final mass would be, we multiply by 0.5 to the power of the number of half-lives. So if we're trying to get the mass after the half-lives, we multiply by 0.5 to the power of the number of half-lives, not power of 12. This gives my answer in milligrams. They want it in micrograms, so I multiply by 1,000 to get it in micrograms. And this is the end of the paper. I hope this was useful to you. Please study whatever you were not familiar with, and good luck on your exams, and thank you for listening.